Okay, so welcome back everyone to our third lecture in the day. Gary, please go ahead.
Okay, thank you. Welcome back to the second lecture for equiangular lines. Last time we saw that we are going to study equiangular lines via Seidel matrices. Just to remind you, these are matrices that look like this: zeros on the diagonal, plus and minus ones on the off diagonal. And some important properties of Seidel matrices, if you want to think about what are the corresponding equiangular line systems, are the eigenvalues. In particular, the smallest eigenvalue, I usually write that as lambda 0. This will be equal to -1 over alpha, where alpha is the common angle of the corresponding equiangular line system. And the multiplicity of this multiplicity is equal to n minus d. So we have all the important parameters, n, d, and the angle, just coming from Seidel matrix. So this second part, we're going to think about enumerating candidates for the characteristic polynomial of a Seidel matrix. So for that, I'm going to write char sub s x for the characteristic polynomial of a Seidel matrix. And today we'll see that these polynomials are very restricted. Yesterday, we saw the result of Neumann that says the smallest eigenvalue, if you have a large set of equiangular lines, this will be an odd integer. And so today we're going to push that a bit further and think about what else we can say, or what more things we can say about the characteristic polynomial of a Seidel matrix. Okay, so the first thing we're going to remember is that we can write a Seidel matrix like this: all ones matrix minus identity matrix minus 2 times a JC matrix of a graph. And if we think about Seidel matrix like that, then we can prove some pretty straightforward results. So the first one is about taking powers of a Seidel matrix. So if we take powers modulo 2, we pretty much just get what we would get if our Seidel matrix is just complete graph. So if I take the kth power of a Seidel matrix and reduce it modulo 2, I'll either get j minus I or n times j minus I. Oops, I broke my chalk. And this is when k is odd, and the second is when k is even. This is pretty straightforward to prove. If you reduce this modulo 2, that the minus 2a just disappears, so you're just dealing with j minus I. And you can push this further to the characteristic polynomial modulo 2. So if I work out the characteristic polynomial of s modulo 2, then again, it's just like working with j minus I. And so we essentially get the characteristic polynomial of a complete graph modulo 2. So this will be either x plus 1 to the n, or x times x plus 1 to the n minus 1, depending on the parity of n. Okay? So again, this is pretty straightforward result, but the implications are actually quite strong from this quite harmless looking congruence. You can already deduce something about Neumann's observation. So for example, if n is even, you know that you can't have any even eigenvalues already just by reducing a modulo 2. And if n is odd, then you know the multiplicity of an even eigenvalue is at most 1. So you get these pretty strong observations or consequences coming from this. And you can even prove stuff like the square root of 2 can't be the eigenvalue of any Seidel matrix. No matter what Seidel matrix you try, you're never going to get it because you'd have an x squared factor somewhere floating around, which we see can never happen. Okay, so that's just modulo 2, but we can go further. So I'm going to just state a useful lemma for us. And this is like a characteristic polynomial shifting lemma. So we'll start off by letting A just be any n by n matrix. And I'm going to write down 2 characteristic polynomials. So first of all, I'll write down the characteristic polynomial of j minus 2 times A. And we'll write that like this. I goes from 0 to n, and we'll use ai for its coefficients. And we'll also write down the characteristic polynomial of a, and we'll give that one bi's for its coefficients, n minus I. I goes from 0 to n. So we have our two characteristic polynomials, and we want to relate their coefficients to each other. So this is our setup, and the conclusion is the r coefficient for the first polynomial can be written in this in terms of the bi's. We have this big power of 2 out front, and then we have b sub r, and then we have this extra slightly annoying factor I minus 1, all ones vector. I goes from 1 to r. So we have this relation, and this lemma can be proved in a routine manner. So I won't go on about the proof here, but a couple of remarks. First one is we have this big power of 2 out front, which we'll see how that's useful later on. Another remark is that here I'm dealing with j minus 2a. The reason for that is just that I kind of disguises some otherwise quite obvious properties that these polynomials have. So I'm dealing with Seidel matrices, but you'll, oh, there's a question?
I'm just throwing your coefficient distributes over both, but there's a parenthesis. They're missing parenthesis.
Oh yeah, I missed parenthesis.
Okay,
Thanks.
cool.
Thanks a lot. Yeah, over the whole thing. So we started off with the Seidel matrix, which has zeros on the diagonal. And now I'm looking at this object, j minus 2a, which just has ones on the diagonal. Because okay, when I apply this, I assume there's zeros on the diagonal, but it doesn't actually matter for this result. But what we'll see later on is that the thing I really am taking advantage of is s plus I. But I stick with s because I'm a big fan of Seidel, and we want to remember his contribution. But I think the key matrices that are kind of helping us out here is really Seidel matrix plus the identity. Okay, so this is a lemma that I'm going to use, and we can use this lemma to get the following result. So here's a corollary of this lemma. So here we're going to let n is going to be an even integer, and A is an adjacency matrix of some n vertex graph, and we write the characteristic polynomial j minus 2a in the way we did before. So just sum I goes from 0 to n, a sub I, n minus I. So this is our setup. We have n is even, A is adjacency matrix of an n vertex graph. This is the characteristic polynomial of j minus 2a. And the conclusion is that 2 to the r divides the rth coefficient. So this is 2 to the r divides a sub r, and this is for all r going from 0 to n. Okay, so now we think about how we get this conclusion. Well, it almost comes immediately from this, because we have this big 2 factor at the beginning. The only thing that causes us trouble is this half. So what we need to do is show that this thing here is even. So how can we do that? Well, so let me give this lemma a name, lemma star. We'll just prove this corollary. So by lemma star, it suffices to show that this 1 transpose a to the I minus 1, 1, 1, all ones vector transpose times a to the I minus 1 times all ones vector. So just summing all the entries of this matrix is even. Oops. Is even. Okay, and that's not so difficult to do. So the case of I equals 1, then we have that 1 transpose a I minus 1 is just n, and n is even by assumption. So we assumed n is even over here. So that gives us the case when I equals 1. When I is at least 2, what happens here? Well, this one is a bit more interesting, and it's a lot of fun to prove this. So I invite you to do it. So this is even, and you can prove this in a few ways, but my recent favorite way to do it is by some handshaking arguments. By, let's just say, handshaking. So if you just shake your hands enough, you'll eventually realize this is even. And so therefore we have this corollary that 2 to the r divides a sub r for all of the coefficients. And this is already enough to prove something very useful. So before I prove the next result, I want to define a particular set. So I define this set that I call script P sub NE. This is my attempt at a script. So this is going to be the set of congruence classes of the characteristic polynomials of Seidel matrices. So this is going to be characteristic polynomial Sx modulo 2 to the e. We're looking at these congruence classes, and we take this over all Seidel matrices of order n, where n is even. Here, I don't need to say n is even at this point. So such that S is I'll just write n Seidel. This just means Seidel matrix of n of order n. So this is a big set of all the possible characteristic polynomials you can get of n by n Seidel matrices. I introduced that, so now I can band the size of this using that corollary. So another corollary is we let n be even again, and we'll fix some exponent e. Then we can say that the cardinality of this script P sub NE is at most 2 to the e minus 2 choose 2. Okay, so we get a nice upper bound on the cardinality of this set. Okay, and the proof, there's not really much to say, but let me just show you how it works. And that's annoying thing sticking out here. So how do we prove this? Well, let's have a look at what this characteristic polynomial looks like. So I take characteristic polynomial of a Seidel matrix, and I give its coefficients names, I equals 0 to n, because it's n by n. And we can write this out. And first of all, we know that this is going to be monic, very obvious. And we can work out the next two coefficients. This coefficient should be n, and the next coefficient is 0. So we know the first three coefficients, so this keeps on going. Why do we know that? Well, we know the trace and the trace squared, or to be more precise, we know that the trace of j, this should be not s, but j minus 2i. So I'm doing a bit of a shift from Seidel matrices to this j minus 2a, because this has nice divisibility properties. It doesn't cause any problems when we count. So if we work out this, we know these because we know the trace of j minus 2a. Well, this just has ones in the diagonal. So here we have trace n. That gives us this minus n. And we also know the trace of j minus 2a squared. That's going to be n squared. And then you use Newton's identities to get the second coefficient of this polynomial. So we already know three of the coefficients. Now let's continue writing out this polynomial. So I'll just rewrite over here. This is x to the n minus n times x to the n minus 1 plus 0 times x to the n minus 2. Now we get into uncharted territory. So this next coefficient is a3, x to the n minus 3, plus and so on, up to a sub e minus 2, x to the n minus e plus 2, plus a sub e minus 1, x to the n minus e plus 1, and so on. So I just go up to this point because we are working modulo 2 to the e here. So all these coefficients, they're going to be 0 mod 2 to the e. And so this is where the interesting stuff happens, the number of possibilities. And here we know that this coefficient is divisible by 2 to the e minus 1 using the corollary. And so how many possibilities are there for this congruence class of this coefficient modulo 2 to the e? Well, there's just 2. And this coefficient, we know that this is divisible by 2 to the e minus 2. So how many possibilities are there? Well, that's 2 squared, or 4, if you prefer. And you can keep doing this argument up to this coefficient here, where there are 2 to the e minus 3 possibilities. Okay, and there's apparently no relation between these, so they can independently change which congruence class they're in, depending on which Seidel matrix I choose. And so in total, total number of possibilities is equal to 2 to the e minus 3 times 2 to the e minus 4, and so on, times 2 to the 2 times 2. And so if you simplify this, you're just adding all these up, 1 plus 2 up to e to the minus 3, which is 2 to the e minus 2, choose 2. And there you go. So this gives us an upper bound on the number of congruence classes possible for the characteristic polynomial of a Seidel matrix modulo 2 to the e. Okay, so the next question is this band sharp? So can we achieve equality in this band? And the answer is, I think so. So this is a conjecture. Well, the answer is yes for some n and e, but I think it's always possible. So the conjecture is conjecture. So if I take for all e at least 2, there exists some natural number, big N. The cardinality of script p n e is equal to this upper band, 2 to the e minus 2, choose 2, or even n bigger than this capital N. This is a conjecture. I don't know how difficult it is to prove this. I believe it's true. And you can check small examples and get equality. I suspect to prove this, you just need to find some infinite family of graphs that hits all the congruence classes. But so far, the infinite families I've tried, of course, haven't worked. Otherwise, it wouldn't be a conjecture anymore. So there's a conjecture. Now, there's a kind of glaring gap in what we know so far, since here we've been assuming n is even. So the obvious question is what happens when n is odd? And so I'll just tell you. So we have a similar theorem. This time we let n be odd. And again, e is just some natural number. And so the theorem is, I don't want to block stuff. So if we assume that, then we get a similar upper bound. That is not as, it's a bit bigger. So the cardinality is at most 2 to the e minus 2, choose 2, plus 1. There's a plus 1 here. So it's kind of the same thing, but you get a plus 1 in the exponent. And this theorem is surprisingly difficult to prove compared to how easy it was to prove the first one. So I won't give a full proof of this because it's a bit tedious, but I will give you some results along the way. So there's a really nice result that we used to prove this, and I want to tell you about that because it's really cool. And for a long time after we found it, it just seemed so nice. Someone must already know it, and eventually we found out that it was already known. But before I give you some idea about the proof, let me state an analogous conjecture. So for this one, we have a similar conjecture, and it's pretty much what you would expect. there's a small technical detail that here we start off assuming E is at least 3. So for E at least 3, the conjecture is there exists some capital N natural number such that the cardinality of this will give equality in this upper bound, which is 2 plus 1, is for large enough odd n, for all odd n strictly bigger than some capital N. So it's what you would expect the conjecture is. So these conjectures are both wide open, so feel free to try to take them down. So next I want to give, because I'm not giving you the proof, I want to give you some ingredient of the proof. And this goes back to Harari and Schwenk. And so just to give you a bit of background on this result, after we found the even version, we were desperately trying to find a good bound for this cardinality. And based on our naive results, we could never get something small enough. We kept doing computations, randomly generating Zeidel matrices, and just desperately looking for some extra relation between the coefficients. The odd case, there is in fact some relation between these coefficients. And this is where Harari and Schwenk come in. So let me just write out these guys' names. This goes back to 1979. And the result that we needed was that if gamma is some graph, and the adjacency matrix we'll call A as usual, and we'll fix capital N to be some even integer at least 4. So they say you have gamma as a graph with adjacency matrix A, N is at least 4, then we have the following congruence. So the sum over D dividing N of phi N over D trace A to the D plus N over 2 all ones vector transpose A N over 2 all ones vector is congruent to 0 modulo 2 times N. So this is, I think, my favorite congruence at the moment. And I don't know if this will ever get knocked off my #1 congruence top spot. I should tell you that this phi here is just Euler's totient function.
The n is independent of the graph.
The n is independent of the graph. This is just some n. And we can think of it's adjacent matrix having small n vertices. So this is any n you like. Euler totient function. This is a kind of amazing congruence, and this somehow tells us a relation between the coefficients that allows us to prove this theorem. But the congruence, maybe you're not so attracted by this congruence at the moment, but once you see the proof, it becomes a bit more attractive, I think. So let me say a few words about the proof, since I found it quite delightful. So how does it work? Well, you let the dihedral group act on closed walks in the graph. So that's the idea. So dihedral group D, not that. Dihedral group D sub n, this acts on closed n walks of gamma. So maybe not so difficult to believe that, since you can just draw a closed n walk as a polygon. And then you can apply Burnside's lemma, or the lemma not due to Burnside, or Frobenius, Cauchy-Frobenius, or whatever you like to call it. Burnside says that if I work out 1 over the cardinality of dihedral group multiplied by the sum over its elements, where we're summing up the cardinality of fix. So the closed walks fixed by the group element G. Well, this just gives you number of orbits.
Script on today.
Gamma. I'm just saying it's
Okay.
fixed, the closed walks of gamma. So I'll say a bit more about this, but the point is, you take this sum, you get an integer. That's the point. And so now I'll just give you some intuition of how this relates to the resulting congruence. So let's do an example. So I'm going to think about what happens when big N is 6. So I'm looking at closed walks of length 6 in my graph. So I can draw that on a hexagon. Here's a hexagon, and the vertices of this hexagon are going to be labeled by vertices in some closed 6 walk. So I'll just label them x0, x1, x2, x3, x4, x5. Okay, so this is some walk in my graph.
Doesn't have to be a cycle, right?
Doesn't have to be a cycle. These edges are not indicating all the adjacencies. So of course we need adjacency here and here, but there might be adjacency here and here as well.
Or a column.
Or equality, yeah, these could be the same. So hopefully this will get a bit more clear when I think about what are the closed 6 walks fixed in gamma by, okay, not just any element, let's look at particular elements. So I'll use R to indicate one rotation round, and so we'll think about the closed walks fixed by R squared, so we're just moving around twice. So that's what we'll think about here. So I'll write down my closed walk again, just like this, 3x, 4, x5, and then back to x0. And now we'll apply R squared to this walk. So if we do that, we're just shifting the indices. So we shift like this, so x0 goes to x2, this becomes x2, and then x1 goes x3, x4, x5, x0, x1, x2. Okay, and if this is fixed by R squared, then these should be equal. Okay, so if this walk is fixed by R squared, then it implies that x0 equals x2, x1 equals x3, x2 equals x4, but we know x2 is x0, so this is equal to x0. What's next? x3 equals x5, which is equal to x1. And so we find that this whole thing is just equal to x0, x1, x0, x1 repeated. x0, x1, x0, x1, x0. How many times do I do this? 1, 2, maybe one more time. So this is what a walk looks like that's fixed by R squared. And so what can we notice about this? Well, this is just a 2 walk repeated 3 times. A closed 2 walk repeated 3 times. So we deduce from this, hopefully from this example, you can see closed 6 walks fixed by R squared are just closed 2 walks repeated 3 times. Fix gamma R squared just consists of closed 2 walks repeated 3 times. Okay, and if you just push this a bit further, or do this in general, you'll see that the fixed k after the k here, so this fixed set for any rotation is described as closed GCD k and n walks repeated over GCD k n times. Okay, and so the next problem is, what's the cardinality? Since Burnside tells us we sum up the cardinality of these fixed sets, well, the really nice thing is you can count these things using the trace of the adjacency matrix. So now I can work out cardinality of this fixed set, well, that's just equal to the trace of A to the G, C, D, K, N. That's really cool. You can get the cardinality of this fixed set in terms of a trace of some power of the adjacency matrix. And of course, there are other objects. There's also reflections here. So instead of writing it out, let's just have a look at what happens. So in this case, when big N is even, there's two kinds of reflections. You have a reflection like this, but the walks that are going to be fixed here, you know that x0 has to be equal to x1. So that means there's an edge from vertex to itself. But here I'm not allowing loops, so I didn't say that, but we ignore loops. So there's 0 elements fixed by this kind of reflection. And the other reflection, this one fixes these two vertices and kind of swaps all the others. And so the walks that are fixed by this are some walk of length n over 2 that kind of goes one way, then reverses. And that's where this term's coming in, because this is looking at walks of length n over 2, and it's just adding them all up, since these will all be fixed by this other reflection. So now, now hopefully you can see that now when I sum up the cardinalities of these things, and on the right-hand side, sorry, keep moving. On the right-hand side, I have an integer. I multiply that up by this, the cardinality of the dihedral group, which is 2n. And so therefore I have this nice congruence. Okay, so that's a really nice tool that maybe you haven't seen before, since I find it very difficult to find this result. And it allows us to prove this upper bound for the cardinality of congruence classes of characteristic polynomials of Zeta matrices. So now I want to briefly summarize what we've seen so far about properties of characteristic polynomials of Zeta matrices. And so I think I want to go to this board. So now I'll introduce polynomials that I call type 2 polynomials. 2 polynomials. And so let me briefly summarize in a theorem what we've seen so far. So we'll let S be a Zeta matrix of order n, so n Zeta matrix. And characteristic polynomial, this time I'm going to write S plus I is equal to this thing. Just give names to the coefficients. So if this is our assumption, then we can say a few things about the characteristic polynomial. So first of all, we can say that A0 equals 1. It's monic, not a surprise. And the next two coefficients we can also write down, minus n, and A2 is 0. We also know that 2 to the I minus 1 divides A sub I, all I 0 to n. So this one I didn't explicitly touch on, but it follows from that lemma where we had 2 to the n, and then there was a half there. So the half reduces the power. So naively, 2 to the I minus 1 divides all of these coefficients. I think I erased that result already. And if n is even, then we can say something a bit stronger, namely 2 to the I divides A sub I for all I going from 0 up to n. So this is just summarizing what we've seen so far. So based on that, we make the following definition. So this is where we define what I call type 2 polynomials. So we say that polynomial Px with coefficient A sub I equals 0 to n. We call this, is called type 2 if, you probably won't be surprised this definition, if 2 to the I divides A sub I for all I going from 0 to n. And we're also going to define a related polynomial called weakly type 2. This is if 2 to the I minus 1 divides A sub I for all I at least 1. Okay, so hopefully you can see that it's natural to have such a definition because the characteristic polynomials we're working with are closely related to such polynomials. So here I'm kind of awkwardly moving from Zyder matrices to Zyder matrices plus I. So I was sometimes tempted to just start again with S plus I instead of using S. But you know, laziness got the better of me. So we have this definition, and now we can write a useful lemma based on this definition.
Using capital sigma, kind of like merge and I and S together. Still like giving credit to Seidel.
Oh yeah.
Save a couple of doctors.
So you mean use a capital sigma here?
Yeah.
Yeah, possibly. Okay, so a lemma based on these definitions is the following. So lemma, we're going to let S be a n-Zyder matrix. So Zyder matrix of order n, and we'll let k be some odd integer. The characteristic polynomial of S minus k times I is weakly type 2. Furthermore, if n is even, this characteristic polynomial S minus k times I is type 2. Okay, so this is not really a mind-blowing lemma, but it's something I just want to keep a record of because we're going to use this pretty soon in a quite important lemma. But before we get on to this crucial lemma, which I'm not sure if I have time to say today, we have a nice property of type 2 and weakly type 2 polynomials, and that's a factorization property. So I'll state it as follows. So the setup is we have P of x is some integer polynomial. Let's assume it's monic. So top coefficient is equal to 1. And suppose that P of x equals Q of x times R of x. Both Q and R are also monic. Sorry, Q and R are both integer polynomials. Obviously, they'll be monic. Then we have the following factorization property. First thing says P of x is type 2 if and only if Q and R are both type 2. So you have this nice factorization property here, and we have a similar one for weakly type 2. So P of x is weakly type 2 if and only if, and this one will need both Q and R are weakly type 2, but that's not enough. So Q and R are both weakly type 2, and at least one of them must be type 2. At least one is type 2. Okay, hopefully that's legible. Okay, and I don't think I have time to move on to my crucial lemma, since it needs a bit of time. It's technical to state, and I also want to prove it. So I'll save that for next time. But before we get onto the next part, I can give you some idea of how all this stuff is going to be used. So why is this factorization so important? So let me take advantage of this time to kind of explain what we want to do. And so remember, the second part is about enumerating polynomials. So what we're trying to do here is we're going to suppose there exists, say, 29 equiangular lines in R14. So we think about what the corresponding characteristic polynomial must look like. So we know already a bit of information about it. For example, we know that the smallest eigenvalue has to be -5, using what we saw last time. It can't be -3 because the lemons is idle classified in that case, and it can't be -7 or more because of the relative band. So we know that the smallest eigenvalue is -5. And so the characteristic polynomial has to have this factor, 29 lines in dimension 14, so the multiplicity is 15. So the remaining factors of this polynomial, let's just call that phi. We want to know what are the possibilities for phi. So this is why we're doing all of this stuff about restrictions for characteristic polynomials of Seidel matrices. And so the trick is we just shift to S plus I and look at the factors there. And so in this case, this will be x plus 4 to the 15, and this will be x minus 1. And so this moves into the type 2 territory that we're looking for. So here, okay, n is 29, and so we know this will be weakly type 2. But this factor, this is type 2. And note that this is type 2. So we can use our factorization theorem, and that tells us that this thing here has to be weakly type 2. Okay, and that's where this factorization comes in. So now we have this degree 14 polynomial. It's weakly type 2. And so that gives us more hope that we can enumerate them. And next time, I'm going to introduce another lemma that tells us more information about this factor, which makes our job of enumerating all the candidates much easier. So we'll see that next time. But I think I'll stop here. And thanks for your attention. And please ask questions if you have any.
Thank you, Gary. Are there any questions?
So how does this shifting?
It's fine.
Oh, so I'm just, you seem very, great facility with shifting S by multiples of the identity. It's not counting blocks anymore. How is this shifting? Can you just assure me that all these things are still valid when I'm adding and subtracting multiples of the identity in the L1's matrix?
Yeah.
There are a couple of changes here, and I just wondered if you would summarize where we have to be careful.
Yeah, there's a few instances where one needs to be careful. Unfortunately, I removed the earlier lemmas, but if we shift by an odd integer, then everything's somehow okay, because in these j minus 2a kinds of things, you'll still get some even things on the diagonal, and modulo 2 they disappear, and so this handshaking stuff still works. And where else does one need to be careful? Yeah, I suppose there's a couple of other places, but one can check the details. It's no problems are encountered. Of course, if you shift by an even number, then there'll be a lot of problems if you shift by even numbers, but shifting by odd numbers, of course, one needs to check that no problems come up. But yeah, I claim it's not an issue.
Okay, thank you.
Yep.
Yeah. So these bounds on the residue practice of the characters and polynomials, I guess we're going to use them next time. Is it to enumerate number of possibilities?
Yeah, good, that's a good question. So I had these strong-looking bounds for the congruence classes of characteristic polynomials of Seidel matrices, but then I perhaps didn't use them to their full extent. So this definition, or this summary theorem, this 2 to the I minus 1 divides the ith coefficient. This is not as strong as our upper bound for the odd case. However, this condition is precisely the same as the upper bound for the even case. So for the even case, we have the full strength here, but you hit on an interesting point, because in the odd case, we're not using the full strength. We're not using the relation between the coefficients, the Harari-Schwenk type stuff. This isn't kind of participating in this result, but we will use this later in a maybe not so elegant way. So yeah, later on, we'll come back to this bound on the number of congruence classes for the odd case. And you'll see that it's done in a slightly clumsy way. So there's maybe an opportunity to like tighten that stuff up. But it's a balance between tedium and utility. So we opted for maybe not the most efficient computational results, but it's a bit more elegant to state. I don't know if you agree, but it's possible to make the results. So there's a lemma I'm going to tell you at the beginning of the next lecture. It's a bit complicated, but you can make it even more complicated, I claim. So it's like not as bad as it could be, but it's a key lemma, and it gives us a lot of power before we start doing computations. So yeah, you're right. The full power of our upper bound isn't being used here for the odd case, but we'll see hopefully see how it comes into play next time.
Is there any hope of characterizing Seidel matrices whose characteristic polynomial is visible by something like x squared plus x plus 1 or some small degree so it's looking at this fine, and rather than go into the database of all possible 5 to degree 14, could you rule out things visible by small degree polynomials?
I'm not sure. So we haven't tried such approaches. I'm not sure how to do that. Yeah, so that could be another way to think about how to do it. So you'll see later on, when we enumerate the possibilities, it's possible that you could kill them off earlier. So I have this enumeration phase, and then the last part of this course will be about the elimination phase. And you can argue that maybe it's possible to eliminate them before you enumerate them, right? So here I'm kind of imposing conditions or developing conditions that makes the enumeration smaller. But maybe I can make it even smaller, maybe as you're suggesting.
Is a typical polynomial in that family is it usable? But how nice are these polynomials?
Yeah, I think they're usually irreducible.
So such a filter wouldn't kill them.
Well, actually, I'm telling a lie. At this point, you can prove that they're always reducible until you get to some point where you can't guarantee any more factors. So next time we're going to show that this has a guaranteed factor of multiplicity, a linear factor of multiplicity 4 as a factor. And it's interesting because the geometric conditions, like the relative bound, gives you geometric conditions on the D unknown eigenvalues. And the closer you get to the relative bound, the stronger these geometric conditions are, and it forces this to be reducible. But as you get further away, the number of irreducible candidates increases dramatically.
What a random polynomial in this P and E, you say that those things are typically reducible.
Yeah, I would say these are typically reducible, yeah.
Okay, so let's thank Gary again.